more physically motivating at least. That is this thing of adding flavors, etc., etc. So let me go where we left. Let me keep up where we left. We said that using these beta functions, one can show that under this deformation, the gauge group 2 is going to go strongly coupled.
Tenemos hasta las 6.
Okay.
Esto está hasta las 6.
Hacemos un break.
Pero
okay. This gauge theory this gauge theory will be such that this goes strongly coupled, this goes weakly coupled, and after one of these cyber dualities, this goes into n minus m, and this goes still in m. Okay? Was this clear, the calculations? Was it more or less understandable here? There is not much to understand, but to believe a lot, right, in the way I was saying it, that the beta functions have this form, etc., the cyber duality, but believe me that all that is very solid things from many years ago. So, what will happen now? So I was saying here, those are the signs for the 1 and 2 groups. And in this case, if one computes it again, it's going to be like this. So it's going to be this group, the one that will go strongly coupled. And this group, the one that will go weakly coupled. And so you will be needing to make a cyber duality of this one, right? That it will give you something like this. And after this, one can see the deformation law immediately. This one will stay in n minus m, because I did nothing there. That was the flavor group. And here what we'll have is an SU n minus m, 2 times n minus m, that's the number of flavors, minus the number of colors. So it's n minus 2m, okay? So I think that from here it's very clear to see that for sufficiently large n compared to m, one can keep many steps going and going and going. Okay? So suppose that those many steps have happened, and then you can fall on different situations. One of the situations is that n is actually larger than m, but a multiple of it. Or it can happen that n is larger than m, but not a multiple. That's some other number, okay? Say 1 or 2 or whatever, right? So all those cases can be studied in detail separately. The case I would like to focus on is this one, in which you fine-tune this deformation m to be a submultiple, let me say, of n, okay? The reason why I will focus on that case is because if you do not do so, the background that I will write should have a singularity, okay? I will write a background describing all this story should have a singularity, okay? So if you see in this case, it's a completely singularity-free, it's a nice background, string background. Okay. So what will happen if n is a multiple of m, right? You will fall into some situation where you will have at some point something like this. Okay, so you subtracted as many times as needed, such that here you subtracted k times, and here you subtracted k minus 1 times, and you will fall into this situation. Okay. If you compute here, you will see that the group 1 is weakly coupled, and the group 2 is strongly coupled. But you should be worried to do cyber duality because the number of flavors to m is not bigger than nc to m plus 1. Okay? Okay? So you should not do there is not a next cyber duality. Okay? This is because nc is 2m, nf is 2 times m, so the number of flavors is equal to the number of colors. Okay? This is okay? Can be seen at least algebraically? Can you see algebraically that you will get from here into something like this and from there to something like that? Okay. So in the first lecture, Luigi Del Devio asked me the following. I was just commenting something about cyber duality as an inspiration for duality, and I said, oh look, suppose suppose that we fix, and I just mentioned it just as an example of duality again, suppose that we fix things such that our number of flavors is always bigger than nc plus 2. Okay? And then we could do a cyber duality, say blah, 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 blah. So Luigi asked me, what happens if it's nc plus 1? I told him, look, in that case you cannot do a cyber duality because you would end up with a field theory with SU nc plus 1, number of flavors, minus number of colors, nc. That's an SU1 theory, that's not a theory. Right? Much worse, if your number of flavors were NC, you should not certainly do cyber duality, because that's not a gauge theory. Right? Okay? For these two cases I was mentioning, there is a particular way of treating them in such a way that you can write kind of a sigma model in terms of mesons and baryons and antibaryons. Okay? So the infrared of this theory is described in terms of mesons, baryons, and antibaryons. For the particular case, NF equals NC. And here again, this is all cyberology. So just believe me this, but this is good thing. For the particular case of NF equals NC, the strong coupling regime of the theory induces on your dynamics a superpotential, or if you want a potential by doing the derivative with respect to the fields, but induces on your dynamics a superpotential such that it tells you that this quantity, this is the meson field, these are the baryon and antibaryon fields, and this is the scale strong coupling of the field theory that you have here, where this thing must be C. Okay, so if you want, this is a Lagrange multiplier. And this is imposing on you that this quantity has to be C. So what will happen with this theory, right, is not a next cyber duality, but the fact that this theory will go very strongly coupled is like an SU2M field theory with 2M flavors. So a potential of this form will be induced on the theory, and there will be different solutions for the infrared dynamics. So just let me tell you what's the physics outcome of the thing, because it's quite interesting. You can show, and I can give you the details if needed, but let me not do it now. You can show that the next step here, when going to the infrared, the description is in terms of an SUM that's coming from this one field theory, supersymmetric, all this is supersymmetric, minimally supersymmetric, plus a Goldstone in the sense of massless supersymmetric multiple. So you see that your infrared dynamics, if you start from up on that stair, and you start flowing to the infrared, believe me that your infrared dynamics will be given by a field theory like this, minimally supersymmetric Young-Mills, given like this, plus an extra particle. It will be supersymmetric, where there will be a massless scalar, a massless Fermi, and then some interactions with this, and of course then interactions with all the rest of the cascade. But that will be your infrared dynamics. Okay.
So is a Vesuminno model coupled to the gauge?
So it is this you want to think it as a Vesuminno model.
Yeah, or not quite.
You may think it in this way. At this level, it's just a Goldstone. Okay. So you're thinking. Why you're saying Vesuminno model?
Well, chiral superfield coupled to gauge.
Yeah, okay. It's a chiral superfield. Certainly, this is a chiral superfield in this sense.
With an
E to the.
Okay, that's.
This is certainly the dynamics. But then there is all the rest of the cascade that will couple via potential. Let me say it this way. Okay. But you see, this theory is interesting in the sense that this theory, at least, will share lots of common interesting things like confinement with phenomenologically interesting theories. Plus the fact that you have a massless particle that might remind you of chiral symmetry breaking. Okay? Though notice that the system here has not a chiral symmetry. This is a Goldstone of that P1 baryonic symmetry that is being spontaneously broken. Just believe me this, and then I can give details to those of you who want.
Does the vacuum moduli space of that theory contain a singularity?
Good.
Your motivation
Of this theory?
Yeah.
Of this theory?
Above in the box, you were keen to avoid.
If I do this, if I do this, right, I will have that. Okay, this is not infrared dynamics first, and what I will have is that there is a moduli space, and that will, as you are saying, will contain a singularity. And the way you may want to think it is that there will be extra eta D3 branes that you can move freely within the conifold. Okay, so I will now explain a bit of that. Okay, right? But if I do this, then I will have a singularity indeed, right? And that singularity will be reflected in the infrared of the field theory that I'll get. Well, I will come here and I will have to study again what's if I'm here, there, etc. Right? And I will have to study it, and that will give me something that will contain a singularity. Okay? This study is done in detail in a paper by Dimarsky, Klebanov, and Seiber. Okay? Very cute paper, difficult to read, but very good. Okay. Okay. So what I should mention briefly is the fact that Klebanov and Strassler were able to write a background, a type 2B background that knows all these things up to here, okay? With which you can compute things like, for example, the masslessness of this particle. Notice that this is a non-perturbative effect. You can compute how this theory is confining, and many other different effects. Okay? So let me, of that background, just to show you that the things become a bit more complicated, let me just try to write it very briefly. I will just write only the metric, but let me just remind you.
One small thing, Carlo.
Yes.
I don't quite see from the field theory side why, I mean, you're adding eta is going to lead to a singular behavior, because it's either, I mean nc plus 1 or nc plus 2 or nc plus 3 or one of these.
So suppose, the thing is that, let me remind how this is. String theoretically, it will be clear the moment you believe me that this eta is an extra number of these three branes that I got that, and I can tell you how in the metric that singularity will appear. If I have this thing, well, one should go back to see what's the dynamics here or there, right?
Yeah.
And study that infrared dynamics. You see what will happen, and this we can think in a moment in the break if you want. That if I'm here or there, etc., I will have a cyber dual description that will be weakly coupled in the infrared. Right? Having a weakly coupled field theory will imply to me that the gravity description should be tricky, right? Because cannot have a weakly coupled field theory, weakly coupled gravity, and that will be your singularity. Okay, but we can think it better in the break. Okay. Good. So let me just remind you how was the metric in the case in which m was 0 and all the thing was not happening. It was something like this. This was 4 dimensions. This was again this radial coordinate rho. So this was your ADS5 space. And then there was this space that I call T11 or the conical. It was something like this, and there was also this 5 form. Okay. So let me say some technicality that is going to be just a way of rewriting this. Okay, but I'm guessing that most of you are familiar with this technicality. But let me just say, there is a nice way of writing 2 spheres and 3 spheres. That is in terms of what are called SU2 left invariant forms, or left invariant forms of SU2.
Sorry, just a moment. That's just the same T11.
Yes, it's the same T11. This is just the upper stage when m is 0.
Okay.
Okay. So I did nothing.
Oh, okay, right. So you're going to.
Yeah. So I'm going to motivate the
right.
thing that will come from. So this is for the case m equals 0. So let me just, for those of you who are not familiar, let me introduce, these are just 3 one forms in terms of triangles that I'm going to call, following that notation, like this. So I'm going to write this in this way. Okay, so these are just 3 one forms. You might be familiar with them or not, but this is just a tricky way of doing the following. Suppose that you do omega 1 squared plus omega 2 squared. So what you will have is, okay, the square of this, double product, square of this, double product. Notice that the double products kill themselves, right? Because you'll have cosine, sine, 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 cosine, sine with a sine. Okay, so the double products kill themselves. While the squares, they sum to 1, and they sum to 1 in this sense. Okay, so this is just. Okay, that's omega 1 squared plus omega 2 squared. If you add to this omega 3 squared, and here again I'm saying something that many of you know very well. This is just a way of writing a 3 sphere. Right? So this was a 2 sphere, and this is just a way of writing a 3 sphere, right? As what people call as a U1 vibration over S2. Okay? And if you want, this is the monopole on the 2 sphere, etc., etc. So this is writing an S3 as an S2 times a circle, but they are fiber, right? So it's not just an innocent thing. Okay, very good. If you allow me that, then allow me to write this thing in the following way. Let me write this thing in the following way. Okay, it's just the same, only that instead of the theta 1 square plus the sine square the theta 2, I just put this thing, okay? And instead of dip psi plus cosine the theta 2, the theta 1 d phi 1, I just put omega 3 plus cosine theta 1 phi 1, okay? So nothing really changed here. Okay, so just let me write the metric in this way. If it's okay, I will erase this line. And I will write here, again, this thing is the same thing. Okay. All right, so that's the metric. That's the metric in the case in which I still did not deform the thing as they are in the cascade. We need that to here. And as I was saying, there is alpha. Good. When you make this deformation, lots of things happen actually. But luckily they were found first by Klebanov and Seitlin, and then the full thing that I will write by Klebanov and Strasler. So let me just write this without much further motivation and discussion. This is what will happen. So what I'm going to write now is the metric that describes this full cascade. First of all, it will happen that you have to turn on a Neve-Schwarz 3-form and a Ramon 3-form. Okay? First of all, this happens. Okay? They are both proportional to m times some 3-form. In this case, this 3-form is the volume of the 3 sphere. In this case, the 3-form is a bit more complicated. Okay? Let me not specify. But to the metric, something quite remarkable happens. That is the following.
Is there an obvious way to see that's what you're turning on? H3 and F3?
Yeah, actually yes. Actually yes. You see, if you put m to 0, okay, so let me try to motivate why you need to turn on these things. If you put m to 0, this is a theory that is a conformal theory, there is an ADS5, etc., etc. So you would say you have, after all, these 3 branes, okay, and these you associate with that F5. Okay? Good. The only tricky point is that these 3 branes are not, like in n equals 4 supergames, just in flat space, right? But they are on the tip of a space that is called the conifold. And by the way, the conifold is this thing here. Okay? This thing there is the conifold. Right? This conifold breaks part of the supersymmetry. That's why the thing has minimal n equals 1 supersymmetry. Okay? And so this is the radial direction of the conifold. This is, if you want, is the S3, and this is, if you want, is the S2 that we are drawing in this way, right? A 2 sphere and a 3 sphere fiber over the 2 sphere. Okay? Good. Now, what you're doing, now is adding to this system, and this is a different way of thinking, 5 branes, such that these 5 branes, they will occupy these directions, and they will be wrapped over this contractible to sphere. Okay? Right? So they are called fractional branes in the sense that they are wrapping a contractible cycle. Now you know that 5 branes, if you describe them electrically, they are associated with an F7, but if you describe them magnetically, they are associated with an F3. Okay? So that F3 is telling you that you have turned on 5 branes. Okay? On the other hand, you know, if you look at the equations of motion of type 2b supergravity, that the Bianchi identity for the 5 form is of this form. Okay, this is the Maxwell equation or the Bianchi identity for the 5 form. So you see, if you are turning on F5 and you are turning on F3, you have to turn on H3 to make this value. Okay, so that's why you turn on the H3. And Klebanov and Seitlin, when they did this, they knew all this kind of trickery, so they know that they have to turn on an H3, and it's part of the art of the thing how to turn it on. What's this? What's that? Etc. Okay. So let me not go over those. But the moment you start getting into details, you start understanding why it has the form that it has to have, etc. etc. All right. But at the motivational level, this is what's happening. Any other questions? Before now, I'm just going to write something here, and we'll close the Klebanov thing. Any other questions or comments? Okay.
Yeah, why do we choose to wrap the S2 and not the S3?
Right, because if you choose to wrap it the S3, it cannot occupy the 3 plus 1 dimensions, but 2 plus 1 of them, it will break your law and something like that. So, let's have 5 branes, right? So, you need it. Okay, so if I were to put it on the 3, 5 branes, so these are 6 directions, right? So it cannot occupy 4 and 3, that's 7. It can occupy 4 and 2. Okay, that's your 6. If it were to wrap this thing, it would be like a wall object in our space. Okay, all right. Okay. So if you want to study domain walls in this kind of system, you can do it by placing some 5 brane on a 3 sphere, and that will behave like a domain wall. Okay. Okay. Any other questions or comments here?
So sorry, on this notion of backgrounds being nice, so I'm assuming all of these backgrounds that are nice always contain a conical singularity, but you mean you don't want them to contain other types of
Very good, very good. This one that I was drawing, this one does contain indeed a conical singularity, meaning that if you compute the Ricci scalar, if you compute they're finite. But the moment you compute this one, this will show you, okay, some divergence. This is 1 over rho to some power, I don't remember. But that in this sense is conical. So this one will contain a singularity. The moment I make the deformation, right, and I follow this deformation up to here, the background that I will draw now will contain no singularity, will be singularity free. And it's singularity free because this theory has a well-defined infrared. There is no any singular point in its modular space, etc. Okay? This one, not this one.
Sorry, sorry. Just a comment here. I mean, what is singular is what looks like the transverse space to the brane. However, it is actually not singular because you get to it, and when you find it in your horizon geometry, which is perfectly regular, is ADS5 cross the T11.
Yeah. But it's true. It's ADS5 cross the T11.
That's a regular.
Okay. Yes. What will be singular is that if I compute the things with the work factor like this, and I have flat space times T11, there I will see.
There I
will see. Okay? Very good. So now comes this deformation that Klebanov and Seitlin started and Klebanov-Strassler finally understood. the metric gets deformed in this way, and let me really not motivate much for how or why it gets deformed in this way. These 4 dimensions are going to be these 4 dimensions here. So you see that what was a simple warp factor now is not a simple warp factor. I'll tell you in a moment what goes there. So let's try to understand. This is a warp factor of that radial coordinate. This is a warp factor of that radial coordinate is the inverse of that one. So whatever was just a simple warp factor ceases to be so, right? Once you turn on these two things, the dynamics is more complicated. You have to go over the equations, but you can find a solution for this. I'll mention it in a moment. So there is a function here and the same function there. You notice that it's good to go to some particular radial coordinate. That implies that you have to turn on a function here. What before was a 1/6, innocent and nice, now it's just a full function. That is this one. What before was a 1/9 is no longer. Is a function that turns out to be the same one as this. There is this difference, if you want. But the most interesting deformation happens in here. and it looks in this way. So these are, what before was omega1 squared and omega2 squared, now pick up a factor that mixes this with these two spheres, right? So you see, at this level, these two spheres was not mixed with that one up in the cascade. The moment you start deforming, you have to mix it. You have to do this, okay? So you are forced to make this mixing, all right? Okay. Okay. So let me say some things that the functions e to the 2k, e to the 2h, e to the 2g are known. Let me not write them. The function a is particularly nice to remember. It's like this, so if you plot it, it's like this. Okay. So what you can see is that if you go to high values of the radial coordinate, or in the language we are developing, high values of the energy, this vibration, this mixing disappears because A goes to 0, and you go into something that will start to resemble this. Okay? and the function h is also known, but up to an integral, right? So it's an integral of a complicated function that one does not know how to do. Okay? So since it's pointless to write exactly the full Klebanov-Strasser background if one is not going to work with it, I would like just to leave it at this level.
So is that h in the e to the 2h the same as the h?
No, sorry. That's in my notation now, it's always like this. Let me call it, sorry. And I call this h hat h in my papers, so I should be faithful to myself, okay? So this is another function, so there is 1, 2, 3, 4 functions, 5, plus one function that appears here. Okay, just bear with me with that. Okay.
Mm-hmm.
So just believe me at this stage that this background contains and knows all these dynamics we were discussing, there is a way of defining gauge couplings. You can define the gauge coupling of the group 1, the gauge coupling of the group 2, in terms of bits of this metric and bits of this H3 and F3, and you can check how one increases, the other decreases, etc., etc. You can check that there is a way metrically plus fluxes to check that every time you go a bit in the radial direction, in this direction, you are changing the ranks in precisely this way, but this is all technology, and I can tell you which papers to read, right? But this is an example where these superficial aspects of the field theory, plus many other aspects, are very cleanly read in a string background. Okay? That is a string background that is completely free of any pathology or any problem. If I do the thing that Paul was suggesting, this keeping this eta, it will happen that this function h will go like 1 over the radial coordinate to some power. So at rho equals 0 will diverge badly. If you do not do that, if you go into this thing, this function h will, in a series expansion, will start 1 plus rho square, etc., etc. Okay, so it will behave very nicely. Okay, all right. So let's cut the Klebanov thing here.
How can you read this number k of times how many cascades from the metric? Is that something?
So something quite nice that you can read in a paper I wrote with Alfonso Ramalho, Felipe Canoura, Francesco Benini, Stefano Cremonesi. It's a very beautiful paper. So if you look for the four of us, there are 2 papers only that we have the 4 of us. So what you have to do in that case, and this is probably something that you are familiar with, not necessarily everyone in the audience, there are different charges one can define in a theory like this one. The tricky point about, so usually when one defines the charge, one has some gauge field. One defines the charge, one defines basically, one looks at the Bianchi identity of this, and one defines the charge as the integral of f, right? So just like you do in the Gauss's law. Theories like type 2b, etc., have in terms of this form that I was saying here, when I was saying that your Maxwell equation looks something like this, has terms that are called Chern-Simons terms. Okay? So when you're in presence of Chern-Simons terms, you could define these that are called Maxwell charges, but there is another charge that you can define. So this is, in this case, the integral of f5. There is another charge that was introduced by Page that is something like this. Okay. It is this charge, the one that when you move a bit, in a control bit on the radial direction, jumps by 1. Okay? It jumps by m, or m, what I'm jumping here. Okay? So this is a very neat story, but it involves calculations, right? So you have to compute it, you have to sit here in this background, do it, etc. But believe me, that's the bottom line of the thing. So since Rishi has to leave and you look very tired, let's break here. And if you want, in the next half hour, and I promise not to keep it to half hour, I'll tell you something about flavors and the Veneziano living and that. So let's cut here.